In this video, we are going to discuss enamine formation, going through its mechanism and the important conceptual details. Now, in the last video, we said that when you're reacting with a primary amine, you're going to form an imine outcome. And the mechanism for imine and enamine formation is identical up until the very last step. When we reacted with the primary amine, the very last step was direct deprotonation of the nitrogen atom to form the imine product, skipping to that last intermediate, the iminium ion. If we started off with a secondary amine, at the iminium ion stage, there is no hydrogen on the nitrogen, and accordingly, we actually get rid of that positive charge on the nitrogen by deprotonating the alpha carbon. We deprotonate the alpha carbon. We remove that hydrogen, and we use the electron density in that carbon-hydrogen bond to form a pi bond between the former carbonyl carbon and the alpha position. And then we broke the carbon-nitrogen pi bond, leaving a nitrogen with the lone pair. So that means that to generate an enamine, we have to have at least one alpha hydrogen. The alpha carbon is the carbon adjacent to the C double bond O. We have to have at least one alpha hydrogen to remove to generate the enamine, because the pi bond in the product is forming between that adjacent alpha carbon and the former carbonyl carbon. So we must have at least one alpha hydrogen to generate our enamine. Coming back to imine formation, because in that last step, we just deprotonated the nitrogen directly, no alpha hydrogen was required to form an imine. But we do require at least one alpha hydrogen to form the enamine. Water is kicked out as a leaving group in the mechanism, and as we've said, that the mechanism of enamine formation is identical to that of imine formation until the very last step. And then we'll talk about this after we go through our initial example, but when we do form that enamine carbon-carbon pi bond, we want that pi bond generated to be the most stable possible if there are multiple options. So let's now get into the full mechanism. We're going to react here with diethylamine and trace acid. Because my neutral amine is a good nucleophile, I'm going to attack right away at the carbonyl carbon and break the pi bond. That generates a tetrahedral structure with a positive and a negative charge. I need to alleviate both of those to get to my hemi-aminal intermediate. So I'm going to protonate my oxygen atom, making that into a neutral OH. I then also need to deprotonate my nitrogen atom, making my nitrogen neutral. Then after I've got my neutral tetrahedral structure, I need to conceptualize of creating a water leaving group. So I will protonate my neutral OH component to make my water leaving group. Now that I have this water leaving group in my structure, I'm going to collapse the lone pair from my neutral nitrogen component, forming a carbon-nitrogen pi bond, and expel my water leaving group. Okay. Now pausing, all of that so far is identical to imine formation. But now that we've eliminated our water leaving group and we've generated this iminium ion, because we started off with a secondary amine, at this stage there is no hydrogen on the nitrogen atom directly. So we have to get creative. We alleviate the charge on that nitrogen atom to form our enamine by eliminating and deprotonating the alpha carbon. So you need to show your amine in solution grabbing an alpha hydrogen. We then use those electrons from the carbon-hydrogen bond to form a carbon-carbon pi bond between the alpha position and the former carbonyl carbon. And then we break the carbon-nitrogen pi bond, leaving the pi electron density there on the nitrogen as a lone pair. Okay. That is where imine and enamine mechanisms diverge. To show you the imine formation mechanism once more, if we started off with a primary amine, we just deprotonate at that nitrogen atom in the iminium ion to get to our final product. And no alpha hydrogen was required, as we're reacting with a primary amine generating an imine. But when we generate our enamine, we need at least one alpha hydrogen. There has to be a hydrogen at the alpha position to remove to generate the enamine product. Okay. Now, if you wanted to just predict the product, combining this ketone with those reagents, what I would do, without thinking through the entire mechanism, is to draw my structure without the carbonyl. I'm then going to singly bond my nitrogen atom to what was the former carbonyl carbon, and then I'm going to make my pi bond between the former carbonyl carbon and the adjacent alpha position. And notice in this example on the left side, I've got a benzene ring. which means that I actually can't form the pi bond on the left side because there's no alpha hydrogen there. No alpha hydrogen. So in this initial example, there was only one place to form the pi bond, and that was to the right alpha carbon. But let's imagine we now take a couple more examples of enamine formation. Here we're reacting with a secondary amine and trace acid. And we recognize that there are two alpha positions. Okay. So in the predicting of a product, we could maybe draw our structure without the C double bond O on the nitrogen visually to where the C double bond O was. And then we have to think about forming a pi bond there or there, because those are our two alpha positions. And both of them have alpha hydrogens that we could remove to form the carbon-carbon pi bond. Now, ultimately, where we form that pi bond in the predominant product is going to be wherever we can achieve the greatest stability. That is our objective. We want to form the carbon-carbon pi bond in the most stable location possible. And here's what we want to consider. We want to first and foremost consider if one of the outcomes is conjugated to another pi system. We would love, and prefer to have a conjugated product over a non-conjugated product. And then if there's maybe no conjugation in either outcome, we would look at the degree of alkyl substitution. But remember, if there's more carbon attachments, we have a more stable carbon-carbon pi bond. So looking at this first example, we could form the pi bond to the left, and that would have a tri-substituted character. There's 1, 2, 3 carbon attachments. If we form the pi bond to the right, that pi bond is only di-substituted. And notice how in this comparison here, neither of the pi bonds is conjugated with another pi system. Because neither of those pi bonds is conjugated with another pi system, we will default to the extent of carbon substitution. I would much rather form my tri-substituted pi bond than my di-substituted pi bond. This left product is the major product because that generated, in this case, the more stable alkene pi bond of my enamine. Looking at the bottom example, I'm again reacting with a secondary amine, and I'm recognizing that there are two alpha positions, both of which have alpha hydrogens. If we imagine the pi bond forming to the left, notice how that's conjugated with the benzene ring. So we have that conjugation, and it's di-substituted. If the pi bond instead forms to the right, notice how the pi bond there is not conjugated to the benzene ring. It is not alternating with the pi bonds of the benzene ring, so it's not conjugated, but is tri-substituted. I would much rather form my conjugated product than my non-conjugated product. That's why in our stability analysis, we prioritize conjugation first and foremost. You would rather form a di-substituted conjugated outcome than an outcome that's more substituted but not conjugated. Okay, that's really key. We prefer conjugation over not having conjugation. So with that being said, I think that's going to conclude this video for enamine formation. Big takeaway though, as you organize imine and enamine formation, is that the mechanisms are identical up until the very last step. In enamine formation, we have to remove an alpha hydrogen, forming that carbon-carbon pi bond. In imine formation, there's no need to remove an alpha hydrogen because we can directly deprotonate the nitrogen atom. And anytime you're reacting an aldehyde or ketone with an amine, you want to ask yourself, am I reacting with a primary amine? If so, I'm forming an imine. If you're reacting with a secondary amine, you will form an enamine. And if you're reacting with a tertiary amine, there will be no net reaction.